Let's know about natural polymers. The most widely used natural polymer materials are collagen, chondroitin, sulfate aggregates. These materials are commercially available with varying composition under the trade name Integra. The other natural polymers for cell support are usually obtained by their aggregation in culture as it occurs in vivo. Example: collagen gels, fibroglue, fibrin glue, matrigel, and some polysaccharides. Among the polysaccharides, chitosan and hyaluronan are used as hydrated gels. The natural polymers mainly act as an on the principle of intermolecular interaction within the polymers to promote intimate molecular packaging. The so formed molecules can effectively serve as support materials. Now let's know about semi-natural materials. Semi-natural materials are derived from the natural macromolecular polymers or whole tissues. They are the modified materials to achieve aggregation or stabilization. Let's know about some examples. First is chemically cross-linked hyaluronan stabilized by benzyl esterification. Second is collagen cross-linked with agents such as tannic acid or carbonamide. Now let's know about design and engineering of tissues. There are There are some surgical criteria are taken into consideration while dealing with the tissue engineering. First is rapid restoration of the desired function. Second is ease of fixing the tissue, minimal patient discomfort. For designing tissue engineering, the source of donor cells is very critical. Use of patient's own cells, that is autologous cells, is favored to avoid immunological complications. Allogenic cells are also used, particularly when the TE means tissue engineering construct is designed for the temporary repair. It is observed that when the cells are cultured and preserved, that means preserved means that is cryopreservation, the antigenicity of allogenic cells is reduced. Another important criteria in tissue engineering is the support material. Its degradation products, cell adhesion characteristics, and mechanical cues. The design and tissue engineering with respect to skin, urothelium, and peripheral nerve are briefly discussed. Now let's know about tissue engineered skin. It was first demonstrated in 1975 that human keratinocyte could be grown in the laboratory in a form suitable for grafting. It is now possible to grow epithelial cells to produce a continuous sheet which progresses to form cornified layers. The major difficulty with tissue engineering skin is the dermal layer, that is processing blood capillaries, nerves, sweat glands, and other accessory organs. Some developments have occurred in recent years to produce implantable skin substitutes which may be regarded as tissue engineering skin constructs. Integra. This is a bio-artificial material composed of collagen, glycose, aminoglycan. Integra is not a true tissue engineering construct. It is mainly used to carry the seeded cells. Now let's know about dermagraft. This is this is composed of polyglycolic acid polymer mesh seeded with human dermal fibroblast from neonatal foreskins. Now let's know about appligraft. This has Human normal fibroblast seeded into collagen gel. A layer of human keratinocyte is then placed on the upper surface. The tissue constructs till now we discussed have limited shelf life, that is about 5 days. However, they can integrate into the surrounding normal tissue and form a good skin cover. Further, there is no evidence of immunological complications with tissue construct engineering. Tissue engineering construct. TE construct. Now let's know about tissue engineered urothelium. It is now possible to culture urothelial cells and bladder smooth muscle cells. This raises the hope that the construction of tissue engineering urothelium is possible. In fact, some success has been reported in the development of a functional bladder in dogs. For this purpose, polymer base, that means polyglycolic acid polymer base, was shaped into a bladder and muscle cells were coated on the outer surface. The luminal surface, that is inner surface, coated with pre-cultured urothelial cells. The bladder constructed in this way functioned almost like a normal one and was maintained for about 1 year. Tissue engineered peripheral nerve implants. Peripheral nerve injury is a common occurrence of trauma and tumor dissection surgery, often leading to irreversible muscle autotrophy. atrophy. Therefore, the repair of injured peripheral nerves assumes significance. The regeneration of the injured nerve occurs from the proximal stump to region at a distal stump. The regeneration is guided by three types of substances. First is conduct materials. This is outer layer conduct material. This is the outer layer and is primary source of guidance. Conduct material is composed of collagen, glycosaminoglycan, that is in short PLGA, polylactic glycolic acid, hyaluronan and fibronectin. All these are bioresorbable materials. Now let's know about filling material. This supports the neural cells for regeneration besides guiding the process of regeneration. Filling material contains collagen fibrin, fibronectin and agarose. Additives. Additives include a large number of growth factors, neurotrophic factors in different forms, combinations, ratios, example fibroblast growth factor, in short FGF, nerve growth factor, in short NGF. Addition of Schwann cells or transfected fibroblast promote nerve generation process. Now let's know about tissue modeling. Research is in progress to create tissue modeling models in the form of artificial organs. Some of the recent development on experimental tissue modeling are now we will discuss. Artificial liver. Let's know about artificial liver. Hepatocytes cultured as spheroids, or hepatocytes and fibroblasts cultured as heterospheroids can be used. They are held in the artificial support system such as porous gelatin sponges, agarose or collagen. Addition of exogenous molecule is useful for the long-term culture of liver cells. Some progress has been reported in creating artificial liver, as is evident from the hepatocytes' three-dimensional structure and metabolic functions. Now let's know about artificial pancreas. Spheroids of insulin-secreting cells have been developed from mucous insulinoma beta cells. Some workers could implant fetal isolates like cell clusters under the kidneys of mice, although the functions were not encouraging due to limitation of oxygen supply. Now let's know about other tissue models. First is pituitary gland. Multicellular spheroids could be created to study certain hormonal release, example luteinizing hormone, in short LH. Following stimulation by luteinizing hormone releasing hormone, that is LH-RH, some success has also been achieved to create spheroids for the production of melatonin. Now let's know about thyroid gland. Thyroid cell spheroids can be used for the study of cell adhesion, motility and thyroid follicle biogenesis. Now let's know about brain cell cultures. Three-dimensional brain cell cultures have been used for the study of neural myelination and demyelination, neuronal regeneration and neurotoxicity of lead. Aggregated brain cells are also used for the study of Alzheimer's disease and Parkinson's disease. Now let's know about heart cell cultures. Aggregated heart cells have been used for the study of cardiac development and physiology. Now let's know about embryonic stem cells engineering. The cells of the body when grown in culture generally maintain their original character. Thus, liver cells behave like liver cells and keratinocytes as keratinocytes. This is possible since each type of specialized cell has a memory of its developmental history. Stem cells are undifferentiated cells that can divide continuously indefinitely to produce daughter cells. The daughter cells undergo differentiation into particular cell types. Embryonic stem cells are an extraordinary class of stem cells that can proliferate indefinitely in culture. As they possess very high developmental potential, the cultured embryonic stem cells, that is in short ES, when put back into the animal can develop into different cell types and tissues. This depends on the site at which they are introduced. For instance, embryonic stem cells in liver adopt the character and behavior of normal liver cells. ES, that is embryonic stem cell cultures to produce differential cells. The ES cells obtained from an early mouse embryo can be cultured indefinitely. The cultures may be continued as monolayer or allowed to form aggregates called embryoid bodies. The cells of the embryoid bodies can specialize and differentiate under suitable conditions by using various combinations of signal proteins into different cells. For instance, when treated with certain growth factors, embryonic stem cells can form astrocytes and oligodendrocytes. These are the main types of glial cells of the central nervous system. Cultured ES cells, cultured embryonic stem cells, appropriately treated with growth factors when injected into the brain can serve as progenitors of glial cells. Thus, it is possible to correct a mouse deficient in myelin forming oligodendrocytes. The grafted cells are capable of forming myelin sheaths around axons lacking them. Now let's know about human embryonic stem cells research. It was in 1998 researchers for the first time reported the establishment of human embryonic stem cell lines. These cells existing indefinitely in culture are capable of giving rise to any human cell type. Now let's know about application of human embryonic stem cells. The application of human embryonic stem cell research are extraordinary. Let's know about the points. Correction of disorders with loss of normal cells, diabetes, Alzheimer's disease, Parkinson's disease, This can be achieved by appropriate cell therapy, engineering, and replacement of various tissues for the discovery of new drugs and testing safety of drugs. The study of development of humans. Limitations of human embryonic stem cells. Let's know about the limitations of human embryonic stem cells. There are several practical and technical difficulties associated with embryonic stem cell cultures and their utility. It is recently found that contamination with medium, the most commonly used being animal derived media, created immunological complications when such cells are utilized for therapeutic purposes in humans. This contamination is identified to be due to a non-human molecule, namely N-glycolyl neuraminic acid. It is suggested that for human embryonic stem cells, culture products of animal origin of any kind should not be used. An ideal alternative is to use human embryo-derived connective tissue cells as the feeder layer in embryonic stem cell cultures. Now let's know about ethical issues of embryonic stem cell research. Many people object to growing of human embryos in the laboratories even if it is limited to the early stages of development. Some countries have in fact banned the use of government funds for human embryo research. However, some private companies are conducting or financing research on human embryonic cells. There are many serious ethical, legal, and political issues surrounding human embryonic stem cell research. This is in addition to the enormous technical difficulties it may take some more years before the appropriate applications of embryonic stem cell research to human welfare becomes a reality. Finally, completed. Any questions regarding this? You can ask me in the comment box and subscribe my channel to know more updates. And this is any people, the students who are preparing for BSc Biotechnology, MSc Biotechnology, and CSR UGC NET can follow my channel. Thank you. And to get also other people who wants to get more knowledge about biotechnological topics can also subscribe my channel. Thank you.